Hello, my name is DDavis. This is a paper that I presented in 2016 at the Australian Acoustical Society conference. It's a method that I developed to optimize the total cost of noise control for industrial buildings by using engineering optimization techniques to minimize the cost of individual components of the buildings. First, we need to understand what optimization is. It is achieving the best possible result with limited resources, or achieving a desired result using the minimum resources, or achieving the best compromise between those two. It's also important to understand what optimization is not. It is not the designer using their own personal preference. So if they use their favorite solutions, that doesn't necessarily mean they've optimized the design. It's also not the designer using their intuition. So an educated guess is not necessarily going to optimize the design result. Some other non-optimal design techniques that might be used would be, for instance, to use the cheapest materials. If you use the cheapest materials, thinking that you will achieve the cheapest overall result, that's not necessarily optimizing the design. If you use the best overall materials with the assumption that you would automatically only need to use less of it to achieve the desired result, that would also not be optimizing the design. You may not achieve the best cost result with that approach. And if you use the most cost-effective materials in terms of dollars per decibel, that's also not necessarily going to achieve the cheapest overall result. Thinking that any of these techniques would achieve the cheapest overall result would usually be wrong. So there are many types of optimization. It's a huge field of mathematics, and many of those techniques are useful in engineering problems. For instance, linear programming, depending on the type of problem, very, very useful. Non-linear programming, integer programming, stochastic programming, all extremely useful for the right applications. Some acoustics problems are particularly suited for using combinatorial optimization, and that's what we'll be talking about in this paper. There are other methods like heuristics and meta-heuristics and constraints functions and all kinds of other types of optimization methods. But today we're talking about a combinatorial optimization method. So combinatorial optimization is just one branch of optimization. Its domain is optimization problems where the set of feasible solutions is discrete or can be reduced to a discrete one. And the goal is to find the best possible solution. So just a quick recap on combinations. If you have 6 objects and you have 2 choices for each object, then you would have 64 possible options. If you have 6 objects and you have 3 choices for each object, then you have 729 options. If you had 4 choices for each of your 6 objects, then you've got 4,096 options. The genetic algorithm is one of the combinatorial optimization techniques. It is based on Darwin's principle of natural selection by mimicking the evolution of life. And the way it works is you create a population of many random guesses. You then breed those elements in the population with each other, and you mutate some of them. You eliminate the worst, and you keep the best, and you repeat, creating new populations. Each new generation gets better and better, and you repeat until the design method converges. So you start with a population of random guesses, you mutate some of them, you create a whole new population, you throw away the worst, you keep the best, and you create a whole new generation. And you go round and round like that through many, many generations until you achieve a convergence of a selection of good results. Now, because it contains inherent randomness, there is no way of knowing that you have achieved the best overall possible result. But the method is robust in that if you run it many times, you will find that it clusters around a general good result, and you can be sure that it is, if not the best, very close to the best. So if we're going to design an industrial building to contain noise, we have a few different properties of materials to play with. we have the transmission loss, the sound transmission loss of the walls and the roof. We have the absorption of the inner surfaces of the walls and the roof and possibly the floor. And we also have cost per square meter of the cladding, which obstructs the transmission of sound through the cladding, and the cost per square meter of the internal absorptive lining inside the walls and on the underside of the roof. So to illustrate with an example, we have a building with a typical design size, length, width and height, and we have some different kinds of material. We have windows in the walls and we have directivity. So if our receiver is in one of these directions, then the sound emanating from these different elements will be attenuated by different amounts as the sound curves around. So if the receiver is over this direction, then there's no attenuation from that wall having to curve around the building, but on the side walls and on the back wall and on the roof, the sound is directed away from the receiver a little bit, so it would need to be attenuated a bit as it travels towards the receiver, and that can be incorporated in the design as well. So if we have a number of different possible cladding materials to choose from for our building, then we can assign the cost per square meter each of those, and we can assign the transmission loss of each of those in terms of RW. So we might have sheet metal cladding, we might have precast concrete panel cladding, we might have straw board, we might have sound absorptive partitions with steel on both sides, we might have other types of composite panels like cold room sandwich panel, and our building might have other elements in there as well. We might also have a lot of different options to choose from in terms of sound absorptive lining to put on the inside of the walls or on the underside of the roof, and each of these walls and roof could of course have different choices. So we might have polyester fibrous insulation, we might have fiberglass insulation or mineral wool for instance, and of course the other elements of the building would have their own absorption coefficients as well. So this is a recording of the genetic algorithm designing this building. It is cycling through a huge number of possible combinations of wall cladding and roof cladding and sound absorptive material lining the inside of the walls and the roof. If the target design noise level was 45 decibels at the receiver, and if you run it 4 times, then you usually get a different result every time. So the first time it was run, it recommended that the 4 walls should have those types, and the internal lining within the walls should be that type, and the roof cladding should be that type, and its internal lining should be that type. And the second, third and fourth time you run it, you get a slightly different recommended design for the building. And each time though, the total cost of the building turns out to be around about the same. So if you choose the cheapest of your runs, then that's pretty much guaranteed to be pretty close to the cheapest possible design of designing that building. And if you change the target design noise level, the genetic algorithm can design alternative wall claddings and roof claddings and internal absorptive lining materials to achieve the target design noise level for, again, the cost optimized result. So again, every time you run it, you get a slightly different answer, and if you choose the cheapest of those, then you can be pretty sure that you've chosen a design of a building which will give pretty close to the cheapest overall possible way of designing this building and achieving that noise level target. So if you continue to change the target noise level at the receivers, then the genetic algorithm can continue to redesign the building, and again you'll get a different answer every time you run it, and choose the cheapest of those. You can be pretty sure that's pretty close to the cheapest possible way of designing this building while achieving that total target noise level result. And if you continue to change the target noise level, the algorithm can continue to find optimized cost results, and as the noise level increases, the cost decreases, as you would expect, but every time it runs, it finds similar answers, and there is a general trend, and the overall comparison is that if you run the algorithm 4 times, then you'll get a similar answer each time for a consistent target noise level, and as the target noise level changes, the costs also change, but no matter what the target noise level is, every time you run it, you get a similar answer. And if you choose the cheapest of all of your runs for each target noise level, then you can be pretty sure that you've designed the building for a cost that's pretty close to the cheapest possible overall cost of designing that building and achieving that target noise level.